How are you? So good to have you here. Let's see. It'll be even better with slides, don't you think? There we go. Well, as we said, my name is Scott Davis. I run a consultancy out of Denver, Colorado called Thirsty Head. I've been traveling here for 7 years now. I understand that it's been difficult for you to get here with all the unrest. Thank you for being here today. I appreciate it. It reminds me of when I was coming here 7 years ago, there was a volcano in Iceland that erupted and was trying to interrupt me coming here. But I'm a huge fan of masala dosa. And so if a volcano can't keep me from coming to Bangalore, mods, certainly a little bit of unrest about water rights couldn't keep me away as well. I've been focusing on web development for, hard to believe now, but over 20 years now. Web development is changing. Now it's hard to discuss web development without speaking about mobile. Mobile in many cases is the primary platform where we consume the web these days. Twitter, almost 80% of its traffic comes from mobile devices. Facebook, 2/3. Instagram, almost 100%. So when we're talking about web development, naturally, this is platform as well. Are any of you in here Angular developers? Angular 2 developers? Yes. We're all waiting anxiously for that, aren't we? Because now, when Angular does finally arrive, we're in what, RC6 right now, release candidate 6? The mobile solutions for Angular 2 are built into the platform. It is not an optional part of the platform. Being able to present web pages that look good and feel natural and usable on smartphones is just as important, maybe even more important than having it appear on laptops and desktops and everything else. So I wanted to start today not talking about any particular technology, but talking about our industry, our craft. There are so many different names we call ourselves. As I met a lot of colleagues, we're all staying at the same hotel as we meet over breakfast. One of the things we ask each other is, are you an iOS developer? Are you an Android developer? I take great pride in saying I'm a mobile web developer, right? But these are how we identify ourselves. These names we use to describe what we do. And it's interesting because it's so important, and yet it's one of the things we do worst in our industry. Naming applications is hard. Naming modules is hard. Naming variables is hard. Yeah? How many of you use foo and bar when you lack better words to describe what you're trying to do, right? Foo and bar have been with us for quite some time. I love calling them syntactic variables because variables that we use. Yes. Oh, absolutely. This is Scott 2.0. Is this better? Is this an improvement? Yes? Wonderful. You always get worried applying a service pack right in the middle of a presentation, right? But this one seemed to work out okay. We were talking about using variables like foo and bar and baz because it is hard to name things. What we do is hard, and we know that names are important. So my team, I just recently accepted a position as Chief Web Architect with a company in Colorado called QSC. And we have a couple of standing rules on our team, and one of them is foo and bar and baz. Those are variables that are okay to say out loud, but never to be written down. Right? Foo and bar and baz are never allowed in our code base. In code reviews, we will look at variable names. Why did you name that X? What did you mean by X? And we find by taking the time to name variables correctly, it helps us understand our code base. It helps us understand what we're trying to do. It's okay to say, well, you take a foo and then you run it through a bar and you get a baz at the other end. But that should be the end of the usefulness of those metasyntactic variable names. Because at some point you want to say, well, we're getting XML announcement UDP packets off of the wire and we need to transform them to JSON and insert them into a CouchDB database. Can you see how foo and bar and baz absolutely lacks the specificity we need in order to have any kind of meaningful conversation? So naming is hard. And talking about what we do is difficult. If you ever tried to explain to a grandmother over a holiday dinner what you do for a living, you understand how complicated it can be, right? And so we fall back on common phrases. And one of them is computer scientist. I like the sound of that. Do any of you identify yourself as a computer scientist in here? Yeah? People who do, I saw a few hands go up in there. Computer science is a scientist who's acquired knowledge of computer science. Any questions? That makes perfect sense, doesn't it? Yeah, all right. Well, maybe not that first sentence, but the latter sentence begins adding a little bit more clarity. A computer science is someone who practices the study of theoretical foundations. Theoretical foundations. The study of what's possible. That's good. That's good. I like the idea of being a computer scientist. Another job title we use to describe ourselves are software engineers. How many of you identify yourselves as a software engineer? Many more hands go up, right? We're the builders, aren't we? We don't have our heads off in the cloud thinking of what's theoretically possible. We implement, yes? So what is a software engineer? A software engineer is someone who applies the principle of software engineering. Any questions? This is easy. I thought this keynote was going to be hard. This is very easy. I mean, Wikipedia is making it just write itself practically. No, a software engineer is a person who applies the principles of software engineering to design, to development, to maintenance, to testing. Yes. How many of you write unit tests in here? I want everyone to raise your hand, even if it's a lie. It's okay. It's okay. Raise your hand. Yes. We all write unit tests, don't we? We all write unit tests. So, how do we describe what we do? If we're not computer scientists and we're not software engineers, what are we? The punchline is in the title of this presentation, but let's work through this. If we consider ourselves scientists, someone interested in the theoretical possibilities of what we do, we can say that you are a person who is engaging in a systematic activity to acquire knowledge. Okay, well that's fine. Again, that's aspirational. But that second sentence, in a more restricted sense, a scientist may refer to an individual who uses the scientific method. And I know that was a punchline a couple slides ago, but now it's really important. I would say that is the definition of what a scientist is someone who uses the scientific method. Which begs the next question, right? What is the scientific method? Do you remember this from school? Yes? My son just entered his freshman year of high school. We said, this is where it begins to count, son. Pay attention, right? And so part of what they learned is the scientific method. And what this means is we can start with general theories and we can make observations about the world. Why is the sky blue? Why does gravity make things feel heavy? And so on and so forth. And while we're spending our time thinking of these interesting questions, what do we end up doing? It's not just big thoughts, but we start thinking of tests. We start thinking of, this is how I think the world works. Let me come up with some tests to see if my hypothesis works. And if your tests pass, wonderful. You say, oh, I think we have a theory now. And if your test fails, you've learned a lot there as well, haven't you? You learned one part of what is not part of how the world works. But in all cases, this idea of testable theory is the key factor of the scientific method. Back in ancient Greece, scientists were philosophers. They would sit back and stroke their beard wisely. Even the women would stroke their beard wisely and think big thoughts. But many times the philosopher aspect of a philosopher scientist didn't mean they had to apply that knowledge in any particular way. They didn't have to test it. They just wanted to make sure that logically they thought it made sense. But very quickly we discovered that one test is worth 1,000 opinions, isn't it? And we want to take these theories, these grand ideas that we have, and apply some scientific rigor to them to make sure that they in fact do behave the way we expect them to behave. And this is not a new concept. We've been doing this scientific method for quite literally thousands of years. So if you consider yourself a computer scientist, you should probably be very familiar with the scientific method it follows. Now, the opposite follows as well. Because how many times have you found yourself having this conversation? Well, here I am, a computer scientist, but I'm having a hard time convincing my colleagues to write unit tests. I'm having a hard time convincing my boss the value of these tests. I'm having a hard time convincing other people that they should be following the scientific method. So, what do you call a programmer who doesn't write unit tests? A computer pseudoscientist, right? Someone who likes the idea of all this rigor of what we apply to, but doesn't want to do any of the hard work. Yeah? Are you a computer pseudoscientist? No, never. So, let's continue this line of reasoning. How many of you are doing Agile in one way or the other back at the office? How many of you are using some form of an Agile methodology? That's wonderful. So you probably end up finding yourselves writing a lot of user stories, right? Use cases, use stories, feature requests. We call them any number of things. Have you ever called them a user hypothesis before? It's kind of interesting. This is something that's beginning to gain a little bit of popularity. Because we said, what if we did try to apply the same rigor to these user stories that we might apply to unit tests and other things? Do any of your user stories look like this hypothesis? We believe that reducing the number of hotel promotions on the front page from 5 to just 1 will result in an increased click-through rate. And we'll know we've succeeded when we've increased the click-through rate by 10% and by 5%. Do any of your user stories begin to apply this level of rigor to what you're trying to accomplish? Not many hands go up, right? Does it end up being more like, I think we need to log into the system? Yeah, logging in, that would be good, wouldn't it? Yeah, and I think it should, I don't know, maybe have a password? Yeah, password, that's what we should have, right? We have the ideas, we have the beginnings of this, but sometimes we don't quite have the rigor we need to follow through. And one of the hardest things we do, beyond trying to name what we do, is know when we're done doing what we think we're doing, right? If you don't have an end goal in mind, if you don't have clear success criteria, how do you possibly know if you're successful or not? In web testing specifically, we do a lot of A/B testing, right? Are you familiar with this? Do any of you do A/B testing back at your office? Yes, of course, right? It's a way for you to test that hypothesis, right? Here's our existing web page that has 12 hotel promotions on it. What if we have another web page that just has 2? What will we do to make sure that our hypothesis works? Do we indeed get more booking? Does the page render more fast? Is it more aesthetically pleasing? Does it just look good, right? But the idea is we're taking one variable there and we are A/B testing it. If it has a value of A, 12 bookings on the home page, what is the outcome? And if it's B, 2 hotel bookings on the home page, what's the outcome right there? And we can see we can begin applying rigor to what we do, rigor that would merit us calling ourselves something as important sounding as computer scientists. So why do scientists only change one variable at a time? That A/B testing, right? You want to change one thing and see if that makes the case. And if it does, wonderful, you're successful. If it doesn't, you change another variable and see if that does things. And sometimes changing two variables at once is in fact what you want to do, but you can't tell if changing both those variables simultaneously is effective unless you know the effect of variable 1 and variable 2. And then by changing them both at the same time, you get a multiplier effect, or you get a negative effect, or you get just a simple additive effect. See, if we're going to be using things like computer science, we can begin applying the rigors of the scientific method to what we do. And nothing of this should sound outrageous, but it certainly is not commonplace. And that's why you come to conferences like this, right? To be inspired to go back and say, why don't we try applying a little bit more rigor to our user stories? Why don't we try changing just one thing? How many times have you come in on Monday morning and said, okay, we need to change the database from Oracle to Postgres and the web framework from React to Angular, and oh, by the way, we're changing the language from Java to JavaScript. Ready, go! How successful do you think you're going to be? Yeah, not very. So part of what we're talking about is how do we measure success? And in computer science, you might think that the numbers are what are important. And I like saying something along this line, that it's not the numbers that are the importance. And said a different way, it's that metrics illuminate. They don't indicate the answer, but they can begin guiding your way towards the answer. There are, in fact, good numbers for you to be tracking and bad numbers to be tracking in your project. Good numbers to track in your project are things like code coverage, cyclomatic complexity. Well, that sounds important, doesn't it? Yeah, these are good numbers to track. These are things that directly correlate to the success of your project. How many of you use code coverage in your project? What does code coverage mean? Code coverage involves, well, writing unit tests, right? And we want to know how much of your code base is covered by unit tests. How much of your code base, how many lines, how many functions, how many if-elses, how many try-catches, how many switch cases are applied. And so this code coverage, it really truly crosses language. If you were in Java, you would be using code coverage tools like Clover or Cobatura. If you are in .NET, you'll be using code coverage tools appropriate for that language and those frameworks. In JavaScript, one that I've found that I like quite a bit is Istanbul. It's a way for you to track code coverage in your code base. And what I love most about it is that they provide you the coverage reports of their own library on their homepage. So this is the code coverage of the code coverage library. It's turtles all the way down, isn't it? Yes. But when we say metrics illuminate, even if you can't read the numbers, even if you can't read the names of the modules they're tracking over there, which one do you think is screaming out for a little bit of attention? It's obvious, isn't it? That big yellow number right there. And so the green numbers, if they're hard to see, they're numbers like 98.71% and 96.22% and 95.35%, right? Do those exact numbers mean anything to you? Is that important? Is 95% measurably better than 94? Is 92.3 worse than 95? Those numbers don't really make sense, do they? What we want is an appropriate amount of code coverage. And so what this report does is say, hey, if you're below a certain threshold, we'll show up in yellow. And if you're below another threshold, we'll show up in red. But it's nice knowing that these indicators leap out at you. This is actually a bit of an information radiator, actually. You don't have to read the numbers. You just get close to this report and you can feel the heat of where you need to focus your attention next. And if we drill into this code coverage. It goes through, and if you see the gutter along the left-hand side, those green bars are each line of your code that's being touched by a unit test. What do you think those big red lines indicate? Methods that haven't been touched by unit tests yet. And if we dig a little bit deeper into these yellow things that are drawing your attention are things like cases. That first yellow blob is a case called both that we haven't covered yet. A few lines down from there, there's a double pipe in there, an or. They're saying read this directory variable in, or just take the current working directory. That's a branch that wasn't covered by a unit test. Later on, there's an error case. If error, then throw this error. And we can see in all the unit tests we've run against our code base, we've never thrown that error before. So all of these are potential bugs looming. And we don't have to read the code, we don't have to analyze the code, we don't have to lex and parse it in our minds. We just kind of look for all the yellow indications that these are branches that maybe we haven't covered yet by a unit test. All the red lines of code that you have neglected to cover. As programmers, we are optimists, aren't we? We tend to write unit tests for the happy path through our code base. And we feel like we have to put a catch block in because our IDE tells us to. How many of you have catch blocks in your code that have / to do as the body of that catch block, right? We know how important those catch blocks are, but if you run code coverage, you will have that subtle nudge you need to write the tests to cover those catch blocks as well. Something as simple as that. As a consultant, as an architect, that's one of the first things I do when I come into a new client, is I run code coverage on their code base. And if they say, well, shucks, we don't have any unit tests, well, that tells you something, doesn't it? But even if they do have unit tests, you run code coverage on the code base, and it illuminates so much. What would you think about a particular module that had tens and tens, if not hundreds of tests written about it? What would you think about a module that had so much testing associated with it? It's important. It's scary. It involves finance. It involves passwords. These are the kinds of things you begin looking. Even though I've never seen your code base before in your life, if I see a whole bunch of tests clustered around something, I say to myself, oh, that's important. Logins, important. Finance, important. Yeah. What do I do if I see modules that have no unit tests associated with them? Unimportant. Or hard to test? Those are two separate issues, aren't they, right? Yes. It's either so important it doesn't merit testing, or it's so difficult we don't have the intestinal fortitude to begin testing it. But again, by running code coverage, it illuminates so much about our code base, and it's such a simple thing to run, and it's available to you in any language that you happen to be working in. So a broader set of analysis can be done. Again, in JavaScript land, I happen to like a project called Plato, because Plato gives you all kinds of interesting metrics about your code base. And all these tools, of course, are free and open source, right? You download them, add them to your grunt script, add them to your gulp script, and away you go. But Plato is interesting because one of the first things it tells you is the total number of lines of code in your code base. And it tells you the average number of lines in any given module. How many of you are paid by the number of lines of code you write in any given day? No? Well, then why would we care about the lines of code in our code base then? What do you think? If something has a lot of code in it, is that better written or worse written than something that has just half a dozen lines of code in it? It's hard to justify long methods when you know that one of the simplest ratios you can apply to your code base is simply the number of bugs in your code base is a simple function of the number of lines of code in your code base. It's really that simple. And while the exact multiplier, the exact ratio varies, we say industry average, there are about 15 to 50 errors per 1,000 lines of code. Microsoft at one point in the 90s when they were talking about Windows NT, they were talking about wanting to have only 10 to 20 defects per 1,000 lines of code. Some people claim that there can be as low as 3 or even 0 lines of code per 1,000 defects. But we can see how that simple metric, something as simple as knowing how long any given method is, you know also how many potential bugs are lurking. I tend to call that the Star Wars effect. Have you ever started reading a method and you keep scrolling and scrolling and scrolling like the beginning of a Star Wars movie? You know, the start of that method fading off into the distance, right? Nothing good comes out of that method, does it? And that's always the method that causes your beeper to ring at 3 in the morning. It's never a half-dozen line method. It's always the epic, yes, that goes on and on. So once again, I've purposely left these numbers small. I've purposely left the text illegible. Which one of these particular functions should you be concerned about? Yeah, it leaps out at you, doesn't it? Those first bars there are complexity bars, and that second bar is source lines of code in there. So as we see small bars and green bars, we feel pretty good about that. That middle method in there, it's a module called ajax.js, right? We have lots of source lines of code and lots of complexity baked into that as well. So as we look at something like Plato, it begins highlighting your code, showing you various metrics. And so if we just look at one particular function, hover over the method name, we begin seeing it has a complexity of about 5. A cyclomatic complexity of about 5. And you start saying to yourself, well, what does 5 mean? I switch into caveman mode when it comes to this. Low numbers, good. High numbers, bad, right? And whatever that low number is and whatever that high number is up for you to decide as an organization. But typically single digits are what you're looking for. And typically single digits in the low variety are even better than single digits of the high variety. Because if we look at this method right now that has a complexity of 5, we start asking ourselves, why does it have a complexity of 5? Well, as we start reading our way through, we have this variable called match. And immediately we say, well, if state equals 2, all right, what else is missing from this code? 1, 3, 4, else? Right? All right, well, we have one break in there if state equals 2. Wonderful. Then what's the next thing? Immediately another if test. If there aren't response headers, okay, here we go, right? And then we build up some response headers. Oh, and then we've got a while, right? So we're going to loop through, and while we try to match all those things, and then eventually we try to either set that to a key or we return null, right? Even though you don't know anything about what's going on with this method, were you able to follow that logic? These are very few lines of code, but high complexity. Is this the code you want to try to analyze at 3 in the morning when your beeper goes off? Probably not. Probably not. So cyclomatic complexity is simply a metric used to indicate the complexity of a program. Thanks, cyclomatic complexity, right? But this is a metric that's been around since the 70s, right? Almost as long as I've been around, and that's old, right? Yeah. So what does this mean? It means if you drop a stone at the top of your function, it goes all the way through and has a single return function at the end. That has a complexity of 1, and that's what you should be looking for. There are no places for those bugs to hide. It's very easy to see the control flow. In this example over here on the screen, we see there are a couple of if-else blocks in there. And so for every one of those potential paths to your code base, I am grossly simplifying the algorithm, but for the sake of illustration here, we can say that that has a complexity of 3 because there are 3 possible paths through that code base. And you can see as those numbers increase, there's more complexity to your code, there are more potential places for those bugs to hide. So low complexity, good, high complexity, bad. Is 4 one worse than 5, though? Is 5 2 better than 7? That's not the point. These aren't metrics that we should be adding and averaging and standard deviating, right? These should be more metrics that illuminate and maybe guide us to potential problems rather than giving us hard numbers. And speaking of hard numbers, there's some hard numbers that we love to track, don't we? Developer velocity is one that comes up in Agile talks all over the place. And some people claim that developer velocity is a managerium, which is simply a unit of measure that exists to produce reports and give decision-making illusions that they know what's going on, right? But really what it boils down to is we tend to track the numbers that are easy to track rather than the numbers that are important to track. And when we talk about things like cyclomatic complexity and code coverage, in fact, those are easy numbers to track as well, just hard numbers to explain, especially to managers. Well, you see, what we have here is the number of possible code paths through the code base, and their eyes droop and they lose interest, right? But what do managers love? They like saying, how many hours did you work this week? Those are easy numbers to understand, aren't they? They're easy numbers to track. I started working on a project and he says, oh yes, it's very easy. We use story points. That's great. We're going to talk about that in just a second. Wonderful, wonderful. He's like, yeah, and I do all the estimation. Okay, usually the developers do the estimation, but you're doing it as the product owner. That's great. And he's like, yeah, and it's very easy. If I assign something a complexity number of like 0.25, that means that I think it should take about 15 minutes to complete. And if I assign something a complexity of 0.5, well, it should take about 30 minutes. And complexity of 1, it should take an hour. And complexity of 2, 2 hours. And complexity of, you get the idea, right? I said, you keep saying that number, that story point, you keep saying that, but I don't think it means what you think it means. He says, well, how else will I know what the progress is of our project if I don't know how many hours people are putting into it? And at that point, the obvious question is, well, if you want to track hours, why don't you just call them hours, right? Story points are meant to help us get past this planning fallacy. And again, this is a scientific theory established in the 70s that says we will always display an optimism bias when we're estimating in time. We need to add 2 new fields to this form. How long do you think it'll take? 30 seconds. Well, what if it takes 5 minutes? Well, what if it takes 20 minutes? What if it takes 45 minutes? Do you really care? No, when you say 30 seconds, what you're trying to do is giving someone an indication of how complex you think the task is. Oh, that's easy. If we weren't talking about it, it'd be done already. All right, well, we need to add an entire email subsystem complete with spam control and aliases and IMAP and POP4 and all that other good stuff. How long do you think that's going to take? I don't know, probably 2 years. Right? What are you trying to convey in that? The complexity of this. And the funny thing is, even if I say I'm 2 years, I'm being optimistic. Do you think that's really going to take me 2 years? No, it's probably going to take me 4, right? So they've tracked this. They've used the scientific method. They've run this through rigorous tests, and some of these numbers are just astounding. They said they asked students to estimate when they would complete these academic projects. Now, these were students who were in this academic process. These are seniors. These are people who've been through 4 years of university, and they asked them to estimate how long it would take. And they asked them to estimate with a 50% confidence, a 75% confidence, and a 99% confidence. Only 13% of the seniors at university were able to predict their success rate with a 50% accuracy. Let me say that again because there are a lot of numbers in there. Only 13% of the estimates came in correct with a 50-50 chance with the coin toss. Only 19% came in with a 75% probability, and less than half, 45% came in when people said, I guarantee you this is when I'm going to get this done. I'm going to bet the farm on this. Less than half the time. And when you take this out of academic studies and to start applying this to real projects, you start seeing there are real dollar values associated with this. The Sydney Opera House was supposed to be completed in '63. It opened a decade later. It was originally estimated to cost $7 million. It ultimately cost $102 million. That's quite a variance, isn't it? Yeah, and I love that last one. I lived through that. My hometown, Denver International Airport, only opened 16 months late. I mean, on a multi-year project, only 16 months is no time, right? That caused an almost $2 billion, with a B, $2 billion, going over budget on those kinds of things. So not only are we really hard at naming things, we're really bad at estimating, aren't we? So why bother? Honestly, we are not going to get better at time-based estimates. We simply are not. So you start asking, why do we care about time in the first place? Do your customers care about time to market? Now, of course they do. You talk to market and say, yes, we got to get to market, we got to get to market, we got to get to market, right? But if we get to market with functionality that doesn't work, does that help? And when you start doing things like, well, can we charge more if we get to market sooner? You start saying, well, maybe time is interesting because it's fairly easy to measure, but maybe it doesn't really have anything to do with what we're trying to get accomplished, right? So really what we should be measuring in our day-to-day jobs is working software. Not developer velocity, not story points, not code coverage, not complexity, right? Working software is what we should aspire to to develop. So this idea of story points were developed in a way to remove time, which we are bad at estimating in, from the equation. A story point is really meant to say how hard it is. Easy, medium, hard. And my team, we use something we affectionately call t-shirt sizing. Small, medium, large. We have 3 points. You can do a 1 or a 2 or a 3. A 1 point means it's going to take a half day or less. And I really don't care if it's going to take 30 seconds or 5 minutes or 15 minutes or 45 minutes or 2 hours or 4 hours. And I really don't even care if it takes 6 hours, right? The idea is a 1 pointer is, yeah, this should take about a half day or less. A 2 pointer is, I don't know, a couple days. A 3 pointer is all week. We do 1 week sprints. And so 3 is the biggest number we can say. I'm going to be working all week on this, right? And so you can see what I'm conveying, and that's about how long it takes us to estimate stories as well. We look at it, it's like, yeah, it feels about half a day. It looks like a 2 to me. That's a 3, that's a 1, that's a 2, that's a 3, that's a 1, that's a 2. We should be able to go that quickly because you ought to be able to make those kinds of knee-jerk reactions. And we do that in everyday life as well. We just had a whole bunch of friends in town a couple weekends ago, my wife and I did, and we wanted to have lunch. We wanted to have everyone over for lunch. And my wife says, oh, I love your barbecued ribs. Can we have barbecued ribs when they come over? I said, we could, but that's an all-day affair. That takes me about 14 hours. And so if we wanted to serve barbecued ribs for lunch, I'd have to get at 1 or 2 in the morning and start cooking. That's a complexity of 3, isn't it? Yeah, I don't want to do that. So what did I respond with? You know, we could just order in pizza and hot wings. That's a complexity of 1, isn't it? We agreed on a complexity of 2. We decided to do hamburgers. We would grill hamburgers, but you can grill hamburgers in 20 minutes, not 12 hours. And we assumed, we negotiated, and that's exactly how it went with my wife and I. And that's exactly how it should go with your project manager and your product owner as well. You should have these kinds of things because as we're estimating stories, the level of complexity also decides how important it is. She said, I love barbecued ribs, but that's really hard to develop. Maybe I'd be happy enough with burgers, which are a 2 instead of a 3. So using these once again, t-shirt sizing, do 2 smalls equal a medium? Does a small and a medium equal a large? The t-shirt arithmetic doesn't work out that way, does it? And neither should story points. They're meant to illuminate, not average and standard deviate. And when people are talking about time to market, a lot of times what I'll do is say, well, let's put continuous delivery in place. Let's say as soon as I'm done with a feature, we will jam that right into production. No waiting, because if that's what's most important to you, Mr. Manager, right? Getting features to market as quickly as possible, let's do it as soon as I'm done. We'll ship it, we'll ship it, we'll ship it. And a lot of times managers will say, oh, all right, slow down. But this is how many websites operate these days. Flickr ends up committing to their website 20, 30, 40 times a day. What version of Google are you using? What dot release of Facebook are you using? What service pack of Twitter are you using? Those version numbers that are important in operating systems and frameworks kind of are less important in websites where continuous delivery is the mechanism they use. So there are a lot of companies using this. Google and Facebook and Twitter, as we said. So we have a lot of things we can do, but would I use continuous delivery if I didn't have 100% code coverage? Would I feel comfortable pushing this to production if I hadn't seen it already passed in my test suite and everything else? So no, we find that testing is a critical part of being a computer scientist. It's a critical part of this. One of the things we did at QSC is we moved from the family vacation model of software releases to the train schedule model of releases. How many of you have had releases that are late? I know that's a silly question, isn't it? One of my clients, I came in, they were 9 months late on one of their quarterly releases. I said, you keep saying that word quarterly release, but I don't think it means what you think it means, right? I said, why haven't we shipped? And they said, well, see, the problem was we were moving from Oracle to Mongo. Well, that caused us to have to rewrite all of our service layer. And then we had to rewrite all of this, and we had to rewrite all of that. And wow, that stinks, doesn't it? What happens if you were able to take that big bang release and begin whittling it down? What if instead of removing all tables from Oracle, what if you started with one table and then went to the next and went to the next and went to the next? See, they were on a family vacation schedule, which means the car doesn't leave until all kids are in the car, right? We can't have just 2 out of 3 kids in our car and call it good enough. We have to make sure everyone's in the car before we leave for the family vacation. The train schedule is completely opposite. And that's what we use at QSC. We cut developer releases every week, every Friday before lunch. And so what happens if your feature isn't quite ready for that release? No big deal. You'll catch the next train. You'll catch the next train. And that has immediately removed all of the stress about us cutting releases. We say, this is the time that we're going to cut a release. And if you're ready, that's great. And if you're not, you'll catch the next train. Do you know how many features we have estimated that have missed 2 consecutive deadlines in a row? 0. We've been doing that since the start of the year. Do features occasionally miss 1 release cycle? Absolutely, happens all the time. They're estimates, right? But none of these estimates, when we're using t-shirt sizing, half day, couple days, all week, none of them are more than 100% off their estimate basis. None of them are more than a week over what we estimate. So just moving to a train schedule release cycle has done wonders for our morale. Because the whole point of Agile is to get into a rhythm. And once you're in the rhythm, it fades into the background and you can ignore it. When do you feel your heart pounding? When everything is going well? No. When you've run up the stairs, or you've run down the hall, or you're running to catch the bus that you missed, right? Those rhythms are off, and that's the illumination that you're looking for. If your heart is pounding, something is wrong. If you're breathing hard and out of breath, something is wrong. This rhythm is meant to make the mundane aspects of our job fade into the woodwork so we don't have to think about it anymore. So we start every sprint on Monday. What are you going to do this week? I think I'm going to do this and this and this. Great. We have daily stand-ups every morning, no more than 10 or 15 minutes. How are you doing? I've accomplished this. I'm working on this. Here are my blockers. And we have this rhythm that comes along. Okay, about Thursday we start talking about we're going to cut a release on Friday. Are you going to make it? Are you going to make it? Yes, no, yes, no, yes, yes, yes. Wonderful. We know what our release is going to be tomorrow. These are the kinds of things we should strive for. And these are the kinds of metrics that allow us to do that. But none of them are hard numbers. All of them illuminate what's good about our project or what's bad. So we spent a lot of time talking about computer scientists and how we're not computer scientists, but we should be. That job title should be aspirational. These are things that we should aspire to be in our day-to-day life. So what about this software engineer? All of you raise your hands with software engineers, so this one should be easy, right? A software engineer or an engineer in general is a practitioner of engineering. Great, we've heard this before. But concerned with applying scientific knowledge, mathematics, and ingenuity. Oh, I like that. As a matter of fact, even the Latin root of engineering is to contrive. I love that. Use that at one of your next software development meetings. I'm going to contrive a login system next week. I love that. But it's to be clever. It's to be clever. And so a lot of times, this is what we think of when we think of software engineering. The clever ones. The clever ones. But when we start reading about the actual definition of what a computer scientist is, this is from the 1960s. A professional engineer is someone who is competent by virtue of her fundamental education and training to apply the what? Scientific method? You mean software engineers have to write unit tests as well? Rats. Yes. Yes, we do. How many of you have seen Neil Ford speak before? He's spoken here in the past. He's with ThoughtWorks, a colleague of mine, very smart. He says that testing, specifically unit testing, is the engineering rigor of software development. And it's kind of interesting because the same punchline applies here, doesn't it? And why did we start calling ourselves software engineers? Well, because we used to call ourselves programmers. I still call myself a programmer. What do? I'm a programmer. I programs, right? But people started associating that as a pejorative term. So they had to involve a little bit of job title puffery. Oh, well, they're programmers over there, but I'm a software engineer, right? I'm better than those programmers. Well, here's another definition of engineering that I like quite a bit. Engineering is the conversion of an idea to an artifact. Wow. Talk about a perfect description of what we do. It engages both the designer and the maker, and it's a subtle process that's always far closer to an art than a science, computer science, right? Yeah. Here's someone else that has made similar conclusions, St. Steve, right? I miss Mr. Jobs. He says that I view computer science as a liberal art. He says there's a tremendous amount of craftsmanship between having a great idea and a great product. As a matter of fact, this is a book that I think should be required reading for everyone in our industry. If you have not read this book, I highly recommend it. I will linger lovingly on this slide so you have an opportunity to write this down. I'm coming back in the spring. Y'all have homework, okay? Y'all have to let me know that you've read The Pragmatic Programmer by Andy Hunt and Dave Thomas. Taking this idea of software craftsmanship to its logical conclusion. Because here we have two identical products that do exactly the same thing. One written by engineers and one written by artists. How many buttons are on that Google TV remote control? Don't answer. It's a trick question. If you turn it over, there's a full 101 key keyboard on the back of it as well. That's an engineering solution right there, isn't it, right? We want to support Netflix. We got a button for that. How about Amazon Prime? Yeah, I got a button for that one too. Yeah? We got buttons for all the services, buttons for all my friends. That's the engineering solution to that kind of thing. So there is quite a bit of art is what we do. And notice that I've gone all this time not talking about languages or frameworks or platforms, haven't mentioned Swift or Objc or Java or JavaFX or any of those other wonderful languages, because really what we do doesn't have anything to do with the language we do it in. I'm going to say that again. What we do has nothing to do with the language that we do it in. If you look at an architect, is that someone who creates buildings or blueprints? The answer is both, of course. But if you ask an architect what she does for a living, what do you think she will answer? Of course, buildings. Blueprints are just a means to the end, not the end itself. So similarly, what do you write? What do you write? Did Mozart write sheet music? Was he known for his penmanship? No, of course not. Wrote beautiful, soaring melodies. So this term of art, polyglot programming. Polyglot, of course, is Latin for many glots, right? Many tongues, many languages. Because what we find is that there are many languages we have to use to be successful. It's not just a matter of choosing the one true language to rule them all, right? It's a matter of understanding the problem and choosing the most appropriate language or framework or persistent solution or platform to solve it on. Donald Knuth, who many consider kind of one of the fathers of computer science. He wrote the book, The Art of Computer Science, not the science of computer science. He's called the father of analysis of algorithms, so he's someone that should feel fairly strongly about software engineering, right? And what is his definition of software engineering? He said, let's change our attitudes on the construction of programs. And instead of imagining that our main task is to instruct the computer what to do, let's concentrate rather on explaining to humans what we want these computers to do. That's from The Art of Computer Programming. It could have been called The Art of Software Engineering, right? If it was written just a decade later. So, similar to computer scientists, we're not engineers, but we should be. This should be something that we aspire to once again. So where does that leave us? We've talked a lot about what we aren't. And in fact, by talking about what we aren't, I've been talking about what we should be. We're storytellers. This is what we've been building up to all this point. Because every aspect of this process involves us not telling computers what to do, but telling other humans what we want these computers to do. Even the quad-core processors we carry around in our pockets and purses these days. As end users, we explain to someone what we want our application to do. All right, when you swipe here, I want to do this. And when it pulls down, I want you to do this. When I press this button, I want it to do this. And if they could do that, you wouldn't have a job, would you? They would be doing it already. So what they're doing as a subject matter expert, they're explaining to you what they want the computer to do. If you consider yourself a computer scientist, you begin talking about what's possible. Well, you know, we could use Bluetooth to accomplish that, or we could use some this or that or the other. We begin exploring the possibilities of what could accomplish that story, that user hypothesis. But we have to do it in a scientifically rigorous way, something that's testable and reproducible and in fact provable. And then once the architects have described what's possible, the engineers turn ideas into artifacts. They write that code. And that engineering rigor that Neil Ford talks about, adding features in a way that, again, are testable and reproducible and sustainable is what a good software engineer does. So I want to ask you a couple of questions as we leave. We've been through this already. If you consider yourself a Java programmer, that's telling, isn't it? If you consider yourself an Objective-C programmer, that's telling, isn't it? Yes. We're here to write applications. In this case, mobile applications. But what does that mean? Does that mean applications on smartphones? Yes. On tablets? Absolutely. On watches? Perhaps. Glasses? Indeed. Car dashboards? Absolutely. But we're here to write applications, and that transcends languages, and it transcends platforms and frameworks. In fact, what we're involved in here is explaining to humans what we want to have happen. Because we have great imaginations, but what we need to do to take these ideas and turn them into artifacts is we need to apply every bit of scientific rigor that we've used for thousands of years in science and geology. It's put probes on planets. It can also put Angry Birds on a phone in your pocket, yeah? But what we have to realize is that we are not scientists. We should be. We're not engineers. We ought to be. But we are indeed storytellers. Did you enjoy yourself? I did as well. Thank you so much for your time.